Alright, so we were doing the backward master equation last day, and then the back from there the backward Fokker-Planck. So what we were looking at, this was just to have a brief recap, we were looking at the probability of being at some state psi at time t, given that you had started at some xi naught at some time t naught, and how does this probability evolve, right? And then you could write two equivalent descriptions. One is the forward, where you say it minus del xi of A1 of xi P of xi comma t plus half del 2 del xi 2 of A2 of xi right. So that would be my forward description, where I am talking in terms of this final state xi, where it is. So this is the forward, or I could write it in terms of the backward, del Tp of xi comma t given psi naught of t naught was A1 of xi naught del xi naught p xi t psi naught t naught plus half A2 of xi naught whole square p of xi t. The difference being that here the derivatives are with respect to the initial state, because you're considering the first step out of where you started from, and so in the backward, whereas in the forward your derivatives are with respect to the final state. So you're looking at just a step before you reach that final step and expanding about that. Okay. So then what we said is that we'll look at first passage times. So we'll look at first passage times. Right. And essentially what we want is the distribution of first passage times f of tau, where the system reaches this final state for the first time, starting from some given initial state. So the interpretation, so this is the probability density. So the interpretation is that f tau d tau is the probability that it reaches xi f for first time. So first time between tau and tau plus d tau, right? So that's my interpretation of probability density for first passage times f of tau, right? And that's what we'll try to work out today. Last day we had done this the mean time, so not formally, but just for the case of the random walk. So let me just keep it here. For the case of the random walk, we had shown that if I calculate the mean first passage time, so tau being integral tau f tau d tau 0 to infinity, that obeys the equation del 2 tau del x naught square equal to minus 1 over d. So we'll see that hopefully that will also come out. All right. So now let me actually write that here, because I keep erasing that. So del 2 tau of x naught. So tau starting from the position x naught with respect to x naught squared times d is equal to minus 1. This is for the range. Right. So, this is the thing that I want, that I start from psi naught. I want to reach psi f for the first time in time between time tau and tau plus t tau. So, let me consider an auxiliary version of the problem, where I say that if my system arrives at psi f, it will continue to stay there forever. Okay, which means that what I am doing is that I am putting an absorbing boundary at psi f. Okay, absorbing boundary. Okay. So, if my system reaches this state, it just stays there. Okay, and then I'll try to calculate the time distribution for when it reaches there. How do I express this mathematically? I express this mathematically by saying that the transition rates out of this state psi f to any state psi is essentially 0, right, for any state. Okay. So, if you are at psi f, you cannot make a transition to any other state. So, it's a way of writing the absorbing boundary condition. All right. So, here let us define this new quantity, which is called the survival probability, which is called as the survival probability. Let me call that S. So, S of t psi f given psi naught t naught. So, let this denote the probability that having started from the state psi naught at time t naught, I have still not reached this absorbing state psi f up till time t. Okay. So, the system has survived essentially. So, that is why it is called the survival probability. Okay. So, it has, so this is the probability that system has not been absorbed at psi f up to time t. Okay. So, this is my survival. All right. So, how do I get this survival probability? So, this survival probability S of t psi f given psi naught at t naught is what? So, the way to think about this is that it has not reached psi f. So, let me think about where all it has reached. So, it could have reached any other state, probability of psi at time t having started from psi naught and t naught, right? And I sum over all of these states which are not psi f. Yes. Yes. No. So, how many ways how have you survived without having reached psi f? You could have survived because you are at state psi 1, that has some probability, you are at state psi 2, that has some probability, and so on. So, the total probability that you have survived without reaching psi f is the summation over all of these probabilities that the system can have reached, right. If I am writing in the continuous representation, I can the survival probability to the first passage probability the distribution of first passage times. Okay, so I have my survival that it has not been absorbed. Now I want to relate this survival to my first passage. So let me say that what is the probability? So what is the probability that we have reached psi f, the state that the absorbing state that you are interested in by time t, by time So, the first passage probability, let us say f of t prime, f of t prime comma xi f having started from xi naught at time t naught. Right. So, this is the probability that I have reached xi f for the first time at time t prime, okay, having started from here. I want to know the probability that I have reached xi f by time t. Then what I would need to do is that I would need to take this first passage and integrate over all of these t primes from 0 to t, right, or not 0, but t 0 since I am writing t. Is that fine? So, this is the probability that I have reached at time t prime. I sum up all of these times up till this time t that I am interested in, and that gives me the probability that I have reached psi prime. Because we are looking at stationary processes, I can also write this as equivalently as f of tau xi f comma xi naught d tau from 0 to t minus t naught. Which probability? This one? Huh? This thing? Huh. No, it is that it has reached xi f by time t. After that, what has happened? We are not. So, has it for the first time reached xi f in some interval of time which is less than t, okay, t minus t naught, whatever. Yes. The survival? Yes. That cannot be written unless? Correct. So, the survival probability is for this in this auxiliary problem we have defined the survival probability. The first passage is general. This is what we have defined is for this auxiliary problem, but the first passage probability that we will calculate will be for the general problem. So, I want to relate this first passage to the A. So, this is the probability that I have reached xi f by time t, which means that the survival, which is that I have not reached xi f up to time t, is nothing but 1 minus this entire probability, right. So, then the survival S t xi f xi naught t naught is nothing but 1 minus this integral f of tau xi f xi naught d tau from 0 to t minus t naught. Okay. And hence, if I want to from here, then if I want to calculate this first passage time distribution of first passage times, what is this? This is nothing but the derivative of the survival probability, because this t minus, let me just write t minus t naught over here, okay, comes over in the integral. So, if I just take this derivative, if I want to write this distribution of first passage times f of tau to reach the final state starting from this initial state, I will take a derivative minus del t of this survival S of t xi f xi naught t naught evaluated at t minus t naught, or let me say just evaluated at tau. Let me either keep a tau or not. So, xi naught t naught. So, then evaluated at t naught plus tau time t naught plus tau. Okay. So, if you have calculated the probability that the system has not been absorbed up till time t, then the probability distribution of times of these first passage times is nothing but the derivative, the negative derivative of the survival probability. I will show this in one more way. That might be maybe better. So let me think about this first passage once more. So again, so this quantity, the first passage, tau xi f xi naught. So this is the probability that it reaches xi f in the time interval between tau and tau plus d tau. So this you can think of therefore as the probability that this particle or process, whatever process, exists before tau plus d tau. So this probability and exits minus the probability that it exits before tau. Okay. So if I think of these two probabilities, that it exits before tau plus d tau, subtract it from the probability that it exits before tau, that leaves me the probability that it exits in this time interval, tau and tau plus d tau, right? But the probability that it exits before tau plus d tau in terms of the survival is just 1 minus the survival, right? Survival up to time tau plus d tau. So this is survival tau plus d tau starting from some xi f. Right. So that is this probability, the first probability, and the probability that it exits before tau is 1 minus s of tau, right? So minus 1 minus s of tau. This is the probability. Sorry, so I should have a f tau d tau over here. Otherwise, this is the probability density. So the probability is f tau d tau. Xi f xi naught, right? So again, therefore, what I have is that this f tau xi f xi naught d tau is s of tau xi f xi naught minus s of tau plus d tau xi f xi naught, right? And therefore, f of tau xi f xi naught. So you divide by d tau, take the limit d tau going to 0 is therefore minus del del tau of s tau. Right. So again, the first passage density is nothing but the negative derivative of this survival probability. This line. So this is the probability that I am reaching. So started from xi naught at time t naught, and I want to reach xi f, and I say that I have reached this in this time interval between tau to tau plus d tau. So that probability is my f tau d tau. Right? So that means that. So now I can break that up into two parts, that I have exited before time tau plus d tau, and I subtract it from the time that probability that is exited before time tau. Then whatever is this difference is that it must have exited between these two time intervals. So here is the probability that it exited before this, here is the probability exited before this. I subtract these two, then it must have exited within that time interval, tau to tau plus d tau. So I just write this in this form, but then I can identify these with the 1 minus the survivals essentially, because survival is that it has not exited up to this time. So therefore, the probability that it has exited by this time is 1 minus survival. Okay. All right. Now, that is the full distribution. Like I said, often very few cases where one can solve for the full distribution, but often it's easier to work in terms of the moments of this probability distribution. So, the first moment is the mean. So, the mean first passage time. So, the mean first passage time, the MFPT, right. So, I want to calculate this mean time tau when it reaches this psi f for the first time, having started from psi naught, whatever. Okay, and that is again just d tau, tau f tau, xi f start 0 to infinity. Okay. Now, this first passage is the negative derivative of the survival. So, this is minus integral d tau tau del s del tau, right. So, I do an integration by parts, first function into integration of the second. So, this is tau s 0 to infinity minus integral of differentiation of the first, so minus integral s d tau. There is a minus plus 0 to infinity, there is a minus here. Is that okay? Just integration by parts. So, what you, and this tau s is from 0 to infinity. At 0, tau is 0. So, this drops off. At infinity, s of infinity is 0, because eventually if you have this absorbing state, it will have reached the absorbing state. So, therefore, this term does not contribute. So, all you are left with is this integral of the survival probability s of that it has survived up to time tau without reaching this state psi f, having started from this state psi naught. Okay. So, one way of thinking about so one way of one way of expressing the mean first passage time is simply as this integration of the survival probability. Okay. So, two things then, the distribution is a negative derivative of the survival, the mean time is the integral of the survival probability. All right. Now, yes. How is that? Because this is from these are my limits, tau equal to 0 to tau equal to infinity. At 0, tau itself is 0. At infinity, s of tau going to infinity is 0, right? Because I have my xi f where I have put my absorbing boundary. So, if you waited long enough, sometime it will come here. So, at infinity, nothing will survive if you waited long enough. So, that is this s tau going to infinity is 0. So, this first term drops out. Okay. So, we have written things in terms of the survival, and what equation does the survival probability obey, right. So, we need to know that in order to solve this. All right. So, note that this probability p xi t xi naught t naught obeys the backward master equation, or the backward, in this case, the backward Fokker-Planck equation, right. And my survival, so let me erase this, but keep. So, I have that f of tau is minus del del tau of s of tau, and mean tau is nothing but integral s tau d tau from 0 to infinity. Suppressing all these psi f, xi zeros and so on, they are all there. Okay. So, my probability p xi t given xi naught t naught obeys the backward equation, and therefore, what my survival, remember my survival s of that I survive up to time t was integral over these p xi t starting from xi naught t naught over all xi, right. And therefore, if I take the derivative of this del del t of s of t, right, this is nothing but del p del t d xi. And for del p del t now I can substitute this, right. So I will get a1 of xi naught del del xi naught of p of xi t xi naught t naught, that is del p del t, and then I have a d xi, that is the first term, and then an integral of half a2 of xi naught del del xi naught of again p of xi t given xi naught t naught d xi. Now these integrals are over xi, and these are a1 and this derivative are with respect to the initial state xi naught. So therefore, I can pull this out, and essentially what I have is a1 of xi naught del del xi naught of integral of p xi d xi, which is nothing but my survival, right. So del del xi naught of s of t. Again, I've suppressed all the other indices, xi f and xi t. And similarly, over here, a2 and this derivative, so this is a second derivative, half a2 of xi naught del 2 del xi 2 del xi naught 2, sorry, of s of t. So this is my equation for the survival. And you see that the equation that the survival probability obeys is nothing but again the backward equation, right? Exactly the backward equation for this probabilities. Because if I have used the forward equation, then these derivatives would have been with respect to xi, right? And then I could not have pulled them out of this integral, and then I would not have gotten the survival over here. I could mathematically there is nothing wrong, of course I can write forward or backward, doesn't matter. But if I use the backward equation, because these coefficients were functions of the initial state in the backward, I can write the survival equation for the survival probability in exactly the same form as the backward equation. Okay, is this clear? So that is why in this whenever we talk about times, when you're interested in times of passage or times of processes, it's the backward equation that is actually more useful than the forward equation. Now, again, this is my survival, but del s del t is nothing but my first passage, right? So f of t, therefore, is let me say minus f of t is then a1 whatever a1 del del xi naught of s plus half a2 del 2 del xi naught 2 of s. And therefore, if I take another derivative, what equation does the first passage density obey? I get del f del t is equal to a1 del del xi naught del s del t, which is nothing but the first passage itself. So therefore, again a1 of xi naught del del xi naught of f of t, right, plus half a2 of xi naught del 2 del xi naught 2 of f of t, right. So the survival probability and therefore the first passage probability both obey exactly the backward equations. And that is why when you're solving these solving for these times, It is the backward equation that is most useful. So, in this backward equation, you can either have P of xi, but you can also have S, or you can have F. It's the same equation that is obeyed by all three of these quantities. All right. Yes. 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 So, I am taking a derivative with respect to time, right. So, del f del t. Here I will have a del s del t, but if I take the minus sign on that side, minus del s del t is nothing but f itself. And again, here I will have a minus del s del t, which is nothing but an f itself. Another way to think about the moments, let me see. Yes. What is the boundary condition of? So, depends on what is of course your setup. So, I solve this subject to the absorbing boundary condition at xi f, right. So, I solve this subject to the absorbing boundary condition at, so think about this. So, for example, I have this random walk process which is doing something, and I want to know that what is the first time it has reached this specific position xi f, right. I will solve this problem subject to this boundary condition, because then after in the original process, of course, the particle reaches here and then continues to do whatever and whatever. I am not interested. I am interested in when does it reach here for the first time. So, I will solve this auxiliary problem, and this auxiliary problem will give me the first passage distribution of the original problem, that it reaches there for the first time. But in order to solve it, I will put a absorbing boundary condition wherever I want my final state to be, right. So, I solve this subject to that boundary condition, that if you reach xi f, then you cannot transition out of xi f. So, again, anyway, I will work out a concrete example. Yeah, I will have lots of time. So, I will work out one concrete example today. Yes, sorry. The rest of the subsequent to that, in the sense that here, so I have put an absorbing boundary condition on this xi f state. You are right that, so until it has reached xi f, nothing has changed with the original problem, right. Once it has reached xi f and I apply the absorbing boundary condition, yes, subsequently things will change. It is no longer the original problem, but I am not interested in that anymore, because I am only interested in the first passage. So, therefore, as long as I am looking at the first passage condition, the fact that I have put this absorbing boundary condition, and therefore, for all future trajectories I have technically changed the process, does not matter to me. It is still the first passage time of the original problem, because no state has come here and then again come back here. I am not looking at paths like that, only the first time. So, therefore, that does not matter. It is still the first passage of the original problem. Is this clear? It's a slightly subtle issue, because we have put in the boundary conditions of this auxiliary problem. The auxiliary problem is not the same as the original problem, but it is same up to the point that my particle reaches there for the first time, which is what I am interested in. What was I saying? Moments. So, another way to deal with, often useful way to deal with this equation is to look at the Laplace transform. Okay, so I have this, I have this. I have the fact that both the survival as well as the first passage obeys the backward equation, which is anywhere written there. So, I can erase this. Now, let us think about the Laplace transform of the survival. So, I write down the Laplace transform. S tilde, all right, of xi naught comma s, s being my the small s, which is my Laplace variable. So, this is s survival probability up to time t, starting from this initial state xi naught, okay, e to the power of minus st dt. All right. So, this is my Laplace transform, the survival probability, and I have my initial condition that the survival probability of yes, so survival probability at t equal to 0 having started from this state is equal to 1. Okay. So started from this state, therefore at time 0 I am definite to have survived. So that is my initial condition. And then I do a Laplace transform of this equation, the equation that the survival probability obeys. So let me just write as S over here, doesn't matter, but whatever, S. Okay. So I do the Laplace transform of this equation. All right. So on the left hand side, I will get small s times s tilde of xi naught comma s minus s at time t equal to 0, which is 1, right. So that's my initial condition. And then here I will just get these s tildes. So is equal to a1 of xi naught del del xi naught of s tilde plus half a2 of xi naught del 2 del xi naught square of s tilde. Okay, so I've just taken the Laplace transform of both sides of this equation. And now note that if I want the mean first passage time, this is s tau d tau or st dt, whatever, which is nothing but my Laplace transform at s equal to 0, right, because e to the power of 0 is 1, so it's st dt. So this is nothing but my Laplace transform of at s equal to 0. Okay. So therefore, the equation for the mean first passage time I can find from this equation. This is the general equation for the Laplace transform. And if I want the equation for the mean first passage time, I can set s equal to 0 in this equation, right. So therefore, if I set s equal to 0, I would get a1 of xi naught del del xi naught of s tilde at s equal to 0, which is my mean time. So mean tau plus half a2 of xi naught del 2 del xi naught square of again s tilde at s equal to 0, which is my mean tau, is equal to, this is 0 because I have a s small s outside, so is equal to minus 1, right. So for a generic process with these jump moments a1 and a2, the equation obeyed by the mean first passage time is this: a1 times del del xi of mean plus half a2 del 2 del xi 2 of mean is equal to minus 1. For the unbiased diffusion, of course, remember, if you are unbiased, your a1 is 0, your a2 is 2d, right. So therefore, what you get is d del 2 del xi naught of t is minus 1, which is nothing but what we had over here last day, right. So for a standard diffusive process, unbiased diffusive process, we recover back what we had gotten from this recursive way of deriving for the random walk. But for any general process, if you can calculate the jump moments a1 and a2, then what you have is this. So this is the equation obeyed by the mean first passage time. You can do this for any moment that you want in principle. So for example, let's say I want the second, so this is the first moment, let's say I want the second moment, right. So let me call that tau 2. Okay. So this is what? So this is integral d tau, tau square, f tau, 0 to infinity. This is my second moment, right? Tau t square f tau d tau. F tau is minus del s del tau, so exactly like we had. So this is integral d tau, tau square, del s del tau minus from 0 to infinity. So this is function integral of the second minus integral of differentiation of the first function. So d tau 2 tau s tau 0 to infinity. And this again, for exactly the same reasons, this term drops off. So you're left with integral d tau 2 tau s of tau, right? And then tau s of tau is like, if I want to write in terms of the Laplace equation, I can take a tau, I can take a derivative with respect to s and then set s equal to 0, right. So this is nothing but 2 times del s tilde, the Laplace transform with respect to s, and then take the limit s going to 0, right, because del s tilde del s is, I will bring down a minus t essentially. So I will have, and then if I set s equal to 0, this will drop off. So I'll have a t st with a minus sign. So it is actually minus. So minus 2 del s tilde del s as s goes to 0. Right? Huh? What is this? Tau 2 is the second moment. So mean is the first moment. We calculated mean is tau f tau d tau. This is average tau square. So let me just write average tau square. Just that, because d tau tau square f tau. Maybe I should not write it below. Above is average tau square. Just the standard way we calculate any moment. All right. So then the second moment is the derivative of this s tilde with respect to s, and then taking s equal to 0. So if I take a derivative of this Laplace transform equation, so this is the equation that is obeyed by the Laplace transform. So if I take a derivative of this with respect to s, I will get s tilde xi naught comma s plus s del s tilde del s, right, and then equal to a1 del xi naught of del s tilde del s, right, and then half a2 del 2 del xi naught square of del s tilde del s, right. And then if I take the limit s goes to 0, so del s tilde del s, take the limit s goes to 0, s tilde. This is clear. So I've just taken the derivative of this with respect to s, so that gives me this equation. Now I want the second moment, tau square average, so which is del s tilde del s as s goes to 0. So I take the s going to 0 limit of this equation. Then s tilde xi naught at s goes to 0 is nothing but my mean time, right. So this is nothing, first term is nothing but my mean time, tau. This term goes to 0 because of this s. Then I have a1 del xi naught of this quantity as s goes to 0 is nothing but my second moment, the thing that I want. So this is tau square average, but with these minus half, so minus a1 by 2, and similarly minus a2 del 2 del xi naught 2. Again, this is my second moment, and So 2, 2, so 4. And you can do this systematically. So you have written down the equation of the mean time, which is this A1 del del xi naught and so on. If you can solve this, you obtain the mean time. If you want the next moment, then the equation for the next moment is this, which is in terms of the mean time. And then if you want the next higher moment, you can take another derivative, and you can continue this order to order up to whatever order you want. In principle, if you solve everything, you have the full distribution. Right. Generally, people stop at mean. If you are more conscientious, they do the second moment, which is the variance. Sometimes you can do the full distribution. But essentially, if you do successive differentiations of this equation with respect to the Laplace variable, you can generate equations for moments up to any order. If you do an nth order differentiation, you will generate the equation for the nth moment. All right. All right. Let me. Is this clear? So this is the setup for the for the first passage time. So these are the equations that we will need to solve if you are interested in first passage times for any process. Okay. So I'll work out an example. Let me copy these somewhere. I'll need the backward, so I'll keep the backward. So my mean time is integral s tau d tau 0 to infinity, which is s tilde of xi naught is equal to 0. That's 1. My first passage density is, of course, the negative derivative of the survival s tau. The equation for the A1 xi naught del del xi naught of the mean time, and these are mean times, remember, starting from xi naught, right, plus half A2 xi naught del 2 del xi naught square of the mean time starting from xi naught. I think that will do. I don't need the second moment for the time. So let's work out one example. So this is the target. I'll talk about the target search problem on DNA. Okay. All right. So what is this problem? So I have my DNA double helix. So I have my DNA double helix. Okay. And it has all your sequence AT, CGs, and so on. Right. So this has your sequence. And let us say I have a protein. I have some protein molecule P that needs to find a binding site on DNA. Let us say this is the binding site for the protein. Once it binds, certain processes can happen. Maybe some gene, maybe there is a gene upstream of over here, maybe there is some gene over here. And then once this protein comes and binds to this site, maybe the gene will start produce protein. Okay. So the protein needs to go and find this target site, where it can bind in order for some biological process to happen. So therefore, the protein needs to find this site, and it needs to find this site on this genome, which is, remember, millions and millions of base pairs long, right? So how does the protein do this search? Nobody knows really, but so ideally, the simplest thing to imagine would be to think that, well, the protein binds somewhere. So the protein comes and binds over here, okay, non-specifically, which means that, so this is non-specific binding, which means it's a weak binding, essentially, non-specific binding. which means that when it is bound to the DNA in this state, it can sort of diffuse along the DNA, slide along the DNA. Okay. So, it diffuses along the DNA. Ultimately, if it once it reaches this target site, it can bind specifically. Which means that the binding energy at this location is very high. So, once it reaches there, it stays there, and then whatever process has to happen happens. Right? So, that is the easiest thing to do, that you do a one-dimensional search along the backbone, along the DNA backbone. All right. Now, the issue is, of course, that if you have a DNA of length L, right, DNA of length L, which is some, I don't know, some millions and millions of base pairs, and you want to scan this whole length of DNA through this sort of a diffusive search, then what would be the time that it would take? Let us say this protein has some, in this non-specific state, it has some diffusion coefficient D1 or D1, which is like 1D diffusion coefficient along the DNA backbone. How long would it take? The time taken to find the target would be roughly of the order of yes, yes. No, in terms of this L, L by D. Who said that, by the way? So, when you have a diffusive search, remember, if you go back to your forward equations and your MSD, x square grows with time, right, t to the power of 1. So, it is not L that appears here, it is L square, right. So, it is of the order of L square over D. Now, of course, you can go and put what is the length of the DNA and what is the diffusion coefficient and so on, and find out an magnitude estimate for the time. And it turns out that, I've forgotten, but it turns out it's many hundreds of seconds, not a few seconds. Okay. And the cell does not have, or maybe even thousands of seconds, and the cell does not have so much time for one single protein to search and find its target. So, you need some way to speed up this process. Okay. So, the most common, again, nothing is certain, but the most common hypothesis is what is called as facilitated diffusion. Is what is called as facilitated diffusion, which says that what you do is a little bit of 1D diffusion like this, but then you do some 3D diffusion as well. All right. So, what does that mean? That means that here is my protein, it binds non-specifically, it does a diffusive search for some time. After some time, it unbinds. Okay, so it comes off this DNA chain and it does some 3D diffusion in the bulk, and then again it meets the DNA chain somewhere. So, it comes here, it binds again, and again it does a diffusive search. If it finds, it finds. If it does not find, after some time it again unbinds, and again it goes and binds somewhere, maybe here, and then it does again a diffusive search, but maybe this time it has bound close enough to the target that you end up finding the target. Okay. So, you can work this out, that if you have these multiple rounds of one-dimensional diffusion and three-dimensional diffusion, what happens to this target finding time, right? And see that whether this strategy is useful or not, whether does it lead to smaller times, or can it lead to smaller times or more optimum search as compared to a pure 1D search. Okay. So, this is the search problem. So, this is what we will try to work out. The setup is clear. Okay. So, now we will just cast it in this whatever language of first passage and so on that we have been doing. There are multiple papers from this. The calculation I will do is from one particular 2013 JP by Wechsler and Kolomaisky. So, this is a 2013 JPCB paper by Wechsler. But again, there are multiple people who have done this. Anyway, so this is the setup, right? So this is my problem, and so I say that, well, so what I say is that, so here is my DNA lattice. Okay, it's a discrete lattice. Each site is a nucleotide. And let us say I have N1 to L. Okay, so it's a lattice with L sites. Out of this, I designate one site as the target site. Okay, so let me call that NF. Okay. So this is, I have N equal to 1 to L. Out of that, one site is the target site that I need to find, which I call NF. And the protein can be either on this chain, or the protein can be in solution. So if it is doing 3D diffusion, it's in solution. So let me call that state as N equal to M. Okay. So this is the solution state. When the protein is not bound to the DNA, but is doing 3D diffusion, let me say that is in the state N equal to M. When it is in solution, it can go and bind to DNA with some rate k on. And let me, for simplicity, assume that it can bind to anywhere on this DNA. Okay, so once it unbinds, it can rebind anywhere on this DNA. And once it is bound, it can to any site. It can, of course, do one-dimensional diffusion, but it can also dissociate from DNA and again go into the bulk with some rate k off. And when it is bound, non-specifically bound to these sites, it can hop either to the left or to the right, let us say with rate u. Okay. So it does diffusive random walk, 1D random walk with hopping rates u. It can, if it is on the lattice, it can unbind with rate k off. If it is in the solution, it can rebind anywhere randomly with rate k on. So this, and let's say it starts with some, it starts at some initial state N naught. Okay, so this is my initial state. So this is the mathematical formulation of this target search problem on a finite lattice. Yes, please. What is N and M? N is the index of this lattice site, small n. So N goes from 1 to L if it is on the DNA. And I have one extra special site which is in solution. So if it is in solution, I'll call it N equal to M. So I have L plus 1 sites available for the protein, L of which are on the DNA, 1 which is in solution. And of course, my basic A is that is P of N comma T having started at N naught at time 0. So this is my basic probability that I am at site N at time T, having started from site N0 at time 0. Okay. All right. So I'll think about times because I'm interested in how long does it take for this target, this specific target to be found. But before I think about times, let me just write down also the forward master equation. Okay. So remember, so let me write down the forward master equation. And this is a discrete problem in that my space is discrete. So instead of writing down the Fokker-Planck, I'll write down the master equation. So del P of, sorry, that has nothing to do with it. Because this is a discrete problem, I'll write down the discrete master equation. Del P N T N naught 0 del T, right? And remember, what is this? So this is, when I write down the forward master equation, it's gain terms minus loss terms. So gain terms are that I come into this state P of N comma T from N naught comma 0 from any other state. So actually I come from any other P of M, and then I have some transition rate to go from that M to N, right? So I am at some site M, that probability times the transition rate to go from that state M to my desired state N. and I sum this over all possible states that I could have come from. This is my gain term, and then I'll have a loss term, which is that I was at the state that I want to be in, P of nt given n naught 0, but then I transition out of that state to any other state. So, n to m, right. So, that is my loss term. So, this is just hopefully to remind you that this is how the forward master is written. So, having said that, so let me say that therefore, I want to write this, that is the generic of course master equation. So, now I want to write for this problem. So, del p del t del p, instead of writing all of this n t and not 0, I will just write n. Okay. So, with the understanding that this is this probability. So, this is p n. Okay. So, for the forward, where could you have come from? What sites could you have come from? N plus 1, n minus 1. So, there will be a p n plus 1 over here, there will be a p n minus 1 over here. Anywhere else you could have come from? Capital M. So, there will be a p m over here. If you were at n plus 1, then what is this transition rate? Is nothing but this hopping rate u, right. So, u, if you were at n minus 1, again it is a symmetric hopping process, plus u. If you were at solution, you can rebind with this rate k on, right. And then what are the loss terms? U into Pn, okay. This is small n, right? Sorry, and then twice, and then k of p. Why capital M? Yes, this is still Pn going out from the n. So, what varies are these, the m is in the rate, so it is Pn. Is that correct? All right. This is my forward master equation, 2u plus k of Pn. This is true of course for all sites between 2 to L minus 1. For the boundaries we must write the special equations, and also for the solution site we must write a special equation. So, this is true for all L minus 1. So, let us write down the special equation for del P1 del T. So, then I need to say that what are my conditions in these boundaries, and let me say that my conditions are that these are reflecting essentially, reflecting both of these, which means that you come here, you can only go back. All right. So, then for P1 I would have u times, you could have come from P2 and you could have come from Pm from the solution, and then you could have gone to, right, and similarly for PL. So, if I write del PL del T, it is u times PL minus 1 plus k on Pm minus u plus k of PL, right. So, that takes care of 1 and L, and then for the solution side, so del P M del T, okay. Where could you have come from? So, what will be the gain terms over here? Yes, what will be the gain term? K of times sum over n 1 to L, right? And what is the loss term? Minus K on P. Well, actually, it is binding to every site with K on. So, it could bind to any site. Actually, let me just keep this K on, let me call these as K on by L. So, let me call these as K on by L. So, let me say that the total binding rate is K on. So, per site it is K on by L. Or if you want to keep this K on, then this should be L times K on, whichever way. K off does not matter because it is, you are at a site and you are coming off. So, it does not. Anyway, here you anyway have to have the sum because it is not just a L. Okay. So, good. So, this is the forward equations. The forward equations are always easy to write. But now I want to, since I want to talk about times, I want to write down the backward equations for these. Okay. All right. So, I want to write down the backward equations for this first passage times. So, let me define, I want to keep this just so I can compare. This is clear, right? Anyway, I am erasing this. If it is not bound, it will be somewhere in the solution. Yes. No, there is an approximation. So, for example, ideally what you want to do is to say that, well, I have my DNA, my protein was bound somewhere here, now it unbinds and it does some 3D diffusion. So, this is some trajectory. Then if it has done 3D diffusion for some time T1 and then it rebinds, then of course, if T1 is small, then I would have a higher probability to bind somewhere closer to where it had unbound from. If my T1 is large, I could have gone to some faraway site. So, in principle, of course, no. This is a simplifying assumption which says that once you have unbound, you have completely lost memory of where you were bound to, and therefore, when you rebind, you bind to any of these with equal probability. It is an assumption, it is not true. It's just a simple, one can do better, but this is the simplest thing, that once you have unbound from this chain, you are now in solution with no memory of where you came from, and therefore, you are equally likely to go in any of these sites. All right. So, now what I want to do is to write down the backward equations. Okay. So, and I want to write down the backward equation for this distribution of first passage times itself, right. So, this is F, what was I calling it? I was calling it NF, right. NF at time t, given that it has started from some site n at time 0. So, this is my distribution of first passage time. So, this I will call again in the same way, I will call this as Fn of t. So, this is the distribution of times t that it takes to find the target NF if it had started from site n. So, that is my Fn of t, and like we said, this Fn of t is just like this S will obey the backward equations, right. And again, I will write the master equation rather than the Fokker-Planck. So, del Fn del t, del Fn del t. Now, there is no gain or loss. So, del t. So, you were at site so let me write for Pn and then I will substitute for Fn, it's the same equation. I'll write the backward equation for Pn. So, this is the first step you take to some site. So, this is NF, let me just have everything here, NFT N0. So, this was sum over everything. Probability that you took your first step out of where you were to some other site. So, N prime The first step takes you from n to n prime, and then from n prime you go to wherever you need to go, nf t n prime, right, 0. And then the other term is that your first step is still at n, and then so you go to p. So you stay at n essentially. So nft n 0. So the same rate. Remember omega. Sum over all n primes. Okay. Sorry, the backward equation sometimes I myself have to look up. So this term, remember, said that in the first step out of your initial state n, you took to some other site n prime, and then from n prime you have to reach the final state. And this term came from this fact that you did not take that first step. So after some time delta t had elapsed, you remained at n, and then from n you went to the final state nf, and this came with this the same rate omega n prime comma n. Huh? Why it is subtracting? So that's what. So here there is, if you think about this final equation, it's hard to sort of like, unlike the forward case, there was no gain and loss interpretations. But if you go back to where we had started out to derive, there, and from there we got this, so that's why I get confused. Remember what had we said, that I had said that you could take this step. So let this stay. So we had said that this del p del t was that you could take this first step in time delta t from, so n prime delta t n 0, and then from this n prime, so from this n prime you go to, in time t you go to nf, right, and then you sum over everything. That was one term. And then the next term was that you did not make this step, which was 1 minus sum over, so plus 1 minus sum over n prime p of n prime delta t n 0. So this was the probability that you did not make this jump, and then you multiplied that by the probability, therefore you go to nf in time t from this initial state, right. And then we had done this Taylor expansion and so on, and we had reached this state. But these final two states does not have that direct interpretation of gain, loss, or so that's why it's one has to think a little bit. But when we had set it up, that it was clear that it makes a jump out to some state. It does not make a jump to that state, the first step. Again, so if you work this out, essentially. You see this summation. So this summation is what gets converted to rates, right? Because there is a probability in time delta t. So this is the rate of going from n to n prime in time delta t. So delta t, right? So that is this probability, and here also this summation is that same thing, that, but it's just that you had this 1 minus, but inside you have the same thing, that omega n prime n delta t. You did not go. So therefore, ultimately once we simplified, the rates that came were the same omega n prime comma n. Unlike in the forward case where it was reversed, remember, n to n prime and n prime to n. In here, because the origin is this term, in one case it went, in the other case it did not go. But the rates that come are the same rates, n to n prime. Is this clear? If not, you should go back to this derivation once more and look at this derivation. But okay, so this is the thing then. So when I'm writing down the backward equation, what I should think about is what is the step that it could have taken out of this initial state, and then what are the rates of that state. And for the second term, it is again whatever you're writing times that rate itself. Okay. All right. So now having said this, so this is my backward master, and like we had shown, I can write this, I will write this next day, del Fn del t will obey exactly the same structure, except instead of P, I will have F everywhere. Okay, so that's what we'll write. But yeah, so just again go back if you want, and if you want me to clarify, I'll do that again. The backward equation in its final form does not have a direct physical interpretation of gain and loss. So you always have to be a little careful when you're writing down the backward equation. It's a bit more tricky than writing down the forward equation. All right, so I'll do this, I'll continue next day.